Welcome to the Silicon Labs webinar. It's covering the Internet Infrastructure Design Challenges. The purpose of the webinar is to share solutions to some of the most common challenges facing engineers like yourselves today when you're working on equipment for the Internet infrastructure. Now we're going to focus on the data center and the cloud. So Ben from Cavium, why don't you touch base a little bit on your new and exciting cloud server SoC that you guys are introducing to the marketplace?
Sure. Thanks, Kyle, and thanks, everybody, for joining the webinar. It's interesting to be called a design challenge, but with advancement in technology comes, I guess, a certain amount of challenges as well. Kyle kind of opened up the webinar by talking about Internet infrastructure and how Silicon Labs is focused on it. And he mentioned broadband, data center, and the core and metro. And what's interesting is, not only are all of these different applications becoming more complex, but they're actually starting to merge, and the lines between all those different markets is becoming very fuzzy. But I think the one thing that Kyle mentioned when he was talking about all of them was bandwidth and intelligence. And so with bandwidth and intelligence, you need fatter pipes, you need more intelligent, you need more efficient compute. And so Cavium thinks we've done a pretty good job at being able to address that with a new processor we have coming up called our Thunder processor. No pun intended with the cloud, but certainly we want to be able to address data center and cloud applications, as there's a lot of moving pieces within that market. And we think that we've put in a couple nice architectural enhancements that can adequately address this market. So if we start looking at the chip, what we've done with this ThunderX processor is at the core of it, there's up to 48 ARM v8 cores. So these are 64-bit cores. Cavium is an architecture licensee. If you're familiar with Cavium, we've actually put out a 48-core MIP 64-bit processor in the past. But for the data center applications, due to some of the software ecosystem, we've made a significant investment to also add ARM into our portfolio. So in addition to the 48 cores running up to 2.5 gigahertz, we have to put very powerful caches in there. So we have a very high set associative L1 cache, as well as 16 megabytes of L2 cache. And then connecting that as well is the opportunity to have a multi-socketed approach, where you can actually have two of these connected in a coherent fashion, where you can have SMP Linux running across two sockets, or just sharing tasks between the two processors. Of course, none of this works without very powerful memory, so we have up to 4 72-bit DDR3 or DDR4 memory controllers. This allows for up to ½ terabyte per SoC. So again, with some of the memory-intensive applications that are coming in just about all of these markets, you need to have the fat pipes, but then you also need to have the compute to handle it, and then the memory and speed of memory to be able to efficiently process that data. In addition, on the I/O side, we have both 10 gig, 40 gig, and 100 gig options, so lots of integration into this device. Typical server chipsets tend to have a multi-chip approach to doing this. Cavium believes in really driving innovation in this market, and so thus we've done a lot of integration with both the GigEs, and then right below that you'll see PCI Express Gen 3. And then we've also implemented up to 16 SATA ports. So with storage becoming a bigger and bigger part of the overall ecosystem and infrastructure, we've integrated 16 SATA ports, so direct connect into the processor. And then we have other I/O for booting and serial connectors and so forth. In the middle of the chip, we've actually also integrated a Ethernet fabric, a standard layer 2, layer 3 fabric that can be used for connectivity and to, again, further integrate the different parts of a data center, a mobile wireless infrastructure platform, or even platforms out on the access side of things, and integrate that further into what we can do with this one processor. We also have security. Cavium's background does come from the security enterprise space, so we've been able to do this for years and years, and we've added that, of course, into this ThunderX processor. And at the very bottom is workload accelerators. These can be everything from big data, indexing, and depending on which type of markets they're going into, can increase performance by anywhere from 2x to 5x, depending on the application. In addition to the SoC, we've also done something called VirtSoC, which basically virtualizes not only the cores, which is the traditional method for virtualization, but we virtualized all the way out to the I/O, so that when you have different guests or VMs or whatever you'd like to run in a virtualized environment, even with containers, you can isolate each of the data paths on the chip to make sure that every guest data is protected all the way through the system. And so that is our ThunderX processor. This is the first part that we'll be coming out with this quarter, and we will also be offering lower core count devices, scaling the family from low core counts all the way up to this 48 core processor. So in terms of the markets we want to address, The first one is obviously the compute space. All of these applications that we're talking about take an enormous amount of compute. And so when we're talking about compute, there's public and private cloud, there's web caching, there's social media, there's graph analytics. There's a huge amount of tasks that need to be done. And we think we've balanced the right amount with compute along with the I/O that can get all those tasks into the processor. The second application we have is storage. So I mentioned that we have the SATA integrated, but in addition to the storage just from the disk side, you also have to be able to move that data in and out. So with the increased capacity of all the SATA drives and SSDs and everything that's coming onto the market, there's a huge amount of data that has to be moved into the SoC to make sure that all of those, I was going to say spindles, but now bytes are going to be written and read at the appropriate time. We also have networking, which has been Cavium's traditional sweet spot. This is where some of the hardware accelerators can come into play in addition to the Ethernet fabric, as well as the powerful cores, as well as the I/O that's integrated into the device. And then we also have a security SKU because, as we all know, with all the things that are happening in the world, encryption is becoming more and more important as we generate more data. We pass it across different pipes. There's different co-locations and lots of sharing where you don't exactly know what the platforms are that are going to be sitting in the middle. So we want to make sure all that data is well encrypted and secured. And that makes up the ThunderX family. All four of these SKUs will be coming out very closely within time to each other. And if you'd like more information on those, we can certainly provide that to you. Of course, as a chip, it's very interesting, but most of our customers are looking for what they can do from a complete board-level solution. So what we've developed is we have two initial reference designs that we have available, and those are a 1U ATX form factor card that comes with the enclosure, as well as a half SSI platform. So you can have two sockets on this single node, and you can do a 4-node system in a 2U platform to be able to get a very compute density and storage all in one single box. Now, this is where the challenges come in. All of the goodness of integration, higher performance, more cores, interconnects between processors, they allow for lots of flexibility in your designs as you go forward with this, but of course you have to be able to manage all of the timing and everything that gets you to be able to make this thing run properly. So with that, I'll turn it back over to Kyle, and he'll talk about how Silicon Labs can address this design challenge number 3.
Thank you, Ben. So moving into design challenge number 3 related to the clocks and the timing. As Ben noted, embedded processors such as the Cavium ThunderX family have many different types of I/O, memory, data bus interconnect options, all of which require high-performance clocks at varying frequencies, formats, and I/O voltages. We call the clock requirements in a system design a clock tree. For a system design utilizing a Cavium ThunderX processor, we have identified 25 clocks that are needed, shown here in the block diagram on the right, comprising of differential as well as single-ended formats. Gigabit Ethernet, 10 gigabit Ethernet, PCI Express Gen 3 clocks are all commonly used in embedded processor designs, all of which require high performance, well below a picosecond of RMS phase jitter. In addition to the high-performance jitter requirements, system-level power consumption is also a growing consideration in system design, especially for the data center equipment markets, which these types of platforms and SoCs are targeting. This clock tree consists of 14 different components to satisfy all of the requirements, including clock generators, buffers, and discrete crystals and oscillators. It is easy to simply place more and more timing components throughout the design cycle as new requirements arise. However, this can get complex and complicated very quickly. The clock solution shown here is not energy efficient, is very expensive from a bill of materials point of view, and very complex from a PCB board design point of view. We present a much more optimized solution here, comprising of Silicon Labs programmable any-frequency clock generators, low-power PCI Express Gen 3 clock buffers, and high-performance universal clock buffers. For the same exact clock tree on the previous slide, we are able to reduce the component count from 14 timing devices down to just 5, while reducing the overall power consumption and increasing the design flexibility and scalability. Silicon Labs offers families of programmable clocks,
such as the 5340-41 that Phil mentioned earlier, clock buffers, as well as low-power PCI Express clock generators and buffers, making it very easy to choose a device that matches your system clock requirements for each design. For example, if system requirements change, you can quickly change the frequencies of a programmable clock generator or choose an 8-output low-power PCI Express buffer versus a 12-output, or upgrade from a 6-output universal clock buffer to a 10-output. Phil introduced our new 5340 and 41 any-frequency clock generators earlier, which support RMS phase jitter down to 100 femtoseconds. Our any-frequency portfolio also includes the SI5338 and SI5350, which are more suitable for embedded processor designs, providing clock outputs for gigabit Ethernet, PCI Express, and other system clocks. These devices support differential as well as single-ended clock formats from 1.8 volt to 3.3 volt core VDD and VDDO, and very wide frequency ranges. We support 2 versions of each device, one that features an I2C control interface for in-system programmability, and the other that supports hardware input pin control, where the devices come pre-programmed from the factory. All of these devices can be configured using our user-friendly Clock Builder software GUI interface, with factory program samples and available in as little as 2 weeks. Our universal clock buffers offer a tremendous amount of flexibility and integrated feature sets, perfect for embedded system designs that need multiple copies of the same frequency. This product family offers user-configurable differential as well as single-ended clock formats on the inputs and the outputs, integrated multiplexers, and supports level shifting to help eliminate external resistor dividers. For this particular Cavium ThunderX clock tree, we have used a dual 1-to-5 buffer supporting the Fanout of 156.25 MHz differential clocks, as well as 50 MHz LV-CMOS clocks, all in the same device. The Cavium ThunderX clock tree solution presented today also included our brand new SI53112 low-power PCI Express Gen 3 clock buffer. This device is part of a whole new family of low-power PCI Express Gen 3 buffers that utilizes our push-pull output buffer technology. We offer devices ranging from 6 to 19 outputs within this new family, which are fully Gen 1, Gen 2, and Gen 3 compliant, with jitter performance well within the max specifications set by the PCI SIG. Let's go into a little more detail on what we mean by low-power push-pull technology for PCI Express clocks, because it presents a lot of advantages over typical solutions available in the market. Most devices today use a legacy architecture called constant current mode output buffers, which does exactly what it says, consuming a constant 15 milliamps of power consumption per output. Coupled with a lower overall core power consumption, our new push-pull PCI Express devices only consume 5 milliamps of current consumption per output, with half the number of external components required, all in smaller form factor QFN packaging. This Cavium ThunderX clock tree example required 11 PCI Express Gen 3 clocks, so using a Silicon Labs push-pull solution saves nearly 400 milliwatts of power just for the PCI Express clocks alone when compared to a traditional constant current mode solution. In addition to that, we can save up to 23 external series resistor components, reducing the overall PCB footprint as well as the bill of materials cost. As a quick summary, embedded processor designs typically comprise of complex clock trees, providing clocks for PCI Express, Ethernet, system, CPU, memory, and other I/O. As bandwidth and speeds increase, so does the need for higher performance clocks. Energy efficiency and low system-level power consumption are also becoming more and more important design factors. Utilizing Silicon Labs programmable any-frequency clock generators, Low-power PCI Express clocks and buffers, as well as our universal clock buffers, greatly simplifies clock tree design, all while meeting and exceeding jitter performance targets and reducing overall system-level power consumption. As shown in this specific example, we've reduced the number of clock ICs required on the Cavium ThunderX design from 14 components down to 5.